All right, so we're going to go back to one of my favorite examples, the one I used for Chubby Dude. Remember Forever Ago, Chubby Chev? The one about ages in Florida, right? So we go back to Florida, and we have all these young people. We have all these old people. This picture came from me walking around and saying, how old are you? I'm 2. Okay, how old are you? I'm 88. Okay, and then plotting those people in here, right? So I had a lot of people that were maybe 18 or something, whatever this age this is. And a lot of people that were up here, maybe 70. You guys kind of with me? How would this picture change if I went out and instead of asking one person, I asked 5 people at a time? Well, let's just go to 50. Let's just go crazy. If I pick 50 people at a time, what's the most likely thing? Let me kind of build up to this. Is it likely that I would get 50 people from right there if I do it randomly? No. What's the most likely thing that would happen? I'd get some young people, some old people, right? In fact, what do we keep saying? If I took 50 people and I took their average, what average would you expect from 50 people? Wouldn't you expect that average, right? If I took 50 people, I expect their average to be close to the actual average, wouldn't I? It's not impossible for me to pick only young people randomly. That could happen, of course. But what's most likely is a mixture. So the most likely thing to happen is to get a few people from there and a few people from there, right? So actually, I'm sorry. Let me make this 20 for right now. So what's going to happen here then is I'm going to have a peak right here that I didn't used to have. This is for individual people. Now I go around and I pick 20 people and I say, what's your average age? Figure it out and tell me. Okay, cool. And I plot that, and I plot the next one, and I plot the next one, taking groups of 20 people. And I'm allowed to repeat people. I'm not going to exclude somebody because I already picked them. They can be there a few different times, right? So what's going to happen then is going to have a peak right here. Right? And actually, it's going to be a little bit better than that. It's going to be kind of smooth. And what else is going to happen is I'm probably going to have a little peak there and a little peak there. And where's those little other peaks coming from? What's the next most likely thing to happen after a mixture? The next most likely thing to happen would be people around here or people around here, right? So I might get a little bump from those. You guys with me so far? Which one of these pictures look more normal? This is not quite normal yet, is it? But it definitely looks a hell of a lot more normal, right? That's the idea. In fact, for anything, I don't care how you draw it, the minute you start taking samples, what's going to be the highest peak? On the mean. And that's going to automatically make it possibly more normal, right? Because where should the highest peak be on a normal distribution? It should be on the mean. Okay, maybe. You guys kind of with me here? Okay, maybe. So now here's the magic number. The minute you get to 30 or above, and this is not true for every single distribution, but it's true for most of them. 30 is good enough. In fact, for most distributions, less than 30 is good enough. But the minute you hit 30 or more, you're guaranteed that the picture you make from the averages from the samples will be normal enough to, for example, use all this data that I want desperately to use, right? Somebody already did all this freaking work. When am I allowed to use this? When it's normal. Shit. So I need to know when is it normal enough that I can use this, right? So in this case, it's at 30. So at 30, it's going to look like that. It's going to be very unlikely to just randomly get 30 people from right there. It's going to be much more likely to get a mixture of people from both sides. So the middle peak is going to be much more pronounced. Okay, how are we sort of doing okay? Let me get this. There's nothing specific I can say about this, but all the ideas are up here. Where do you think the smallest standard deviation is? Which one would have the smallest standard deviation? Let's say this is 1, 2, 3. Which one has the smallest standard deviation?
3.
3, good, exactly. Because what do all the sample means do? They kind of rush to the middle, don't they? Because every time I take a sample, I expect it to have the average. Right? So if the average age at Grossmont is 27, and you take 30 kids from Grossmont, what's your best guess for the average going to be for those 30 kids? 27. Are you freaked out if you get 26? No. 28? No. If you get 50, you're like, holy shit, how did I pick this? Right? It's not impossible, but it's really unlikely. Maybe you picked at the wrong time of day. You only picked at 7 o'clock at night or something, right? You're like, oh, crap, I didn't pick very well. You guys kind of with me? Okay.
No, go back over that one again.
Oh, shit. Okay.
Just this one part. Not the part about the 50.
So the point about, so if I took 50 Grossmont students, and you had to guess at what the average age was, my best guess would be the average age of all Grossmont students. Right? Especially if they're randomly selected.
Okay.
If they're randomly selected, their average age should be close to the actual average age.
Okay.
So isn't that what this picture is saying? Where are most of my samples? Close to the real average. It's not impossible to pick 50 really young people or 50 really old people. That's what the picture also says. It just says it's really, really unlikely. How we doing? So the neat thing is, no matter what shape you start with, I don't care what shape you draw here, the minute you get up to 30, it's going to be looking like this.
You have to be close, like the bell curve, right?
Yeah, it's going to be bell curve at 30 or even sooner than 30. For most things it's sooner, but we just say 30 to be safe. So when I have a sample of size 30 or more, what am I allowed to use for probabilities? This dude, right? It's full of freaking probabilities. I desperately want to use this stupid thing, right? I don't have to do all this work myself, doing some weird... If it's not normal, it gets really freaky. So please let it be normal so I can do this. Okay. So let's do a concrete example.
So can I ask you a dumb question?
Yes.
For number 1, there's no way you could use this to in here, right?
Mm-mm.
Okay.
Definitely not. The best I can do for number one is to use what? For probabilities. What works no matter what? Chubby dude, right? Chubby chef.
Okay.
Even for 20, it's a lot more normal, but I still can't use that chart. I still have to use Chubby Chev at the best. And Chubby Chev is not very powerful. The minute it's at 30 or more, I'm allowed to use a chart. It's assumed to be normal enough. Cool. The bigger your sample gets, the more normal it gets. Okay. So we got this here? Okay. Turn this dude off.
Are we in the 6-4 stuff now?
Oh yeah, 6-4 stuff. So let's say I have in a hat, as has to happen in statistics at some point, we have in a hat the numbers 1, 2, 3, 4 written on paper, right? If I pick one of them out, can you make a little chart like this for me? Picking one number out, what could you get?
1, 2, 3, or 4.
I like it, right? It's pretty simple. The values you could get is here. What are the probabilities of each of those?
1 over 4.
1 out of 4, right? You got a 1 out of 4 chance of getting any of those. They're all equally likely, right? If I mix it all up, 1/4, 1/4, 1/4, 1/4. Quarter, yeah. So you can make it 0.25 all the way down. Okay. So what would that look like if I made a histogram out of this thing? It would look really boring. How tall would all the rectangles be?
The same.
Same height. In fact, who knows from the homework what this thing is called then?
A box. I forgot.
Not a box. I like it though.
That's a box.
Uniform distribution?
Uniform distribution. I love it.
That's right. It's a box.
This is 0.25. That's a decent name for it. It's uniform, right? So rolling a die has a uniform probability as long as it's not a weighted die. They all have a 1 out of 6 chance of happening. Right, it's a good example of uniform probability. How are we doing so far? We all right? Does that look normal?
No.
Hell no. Now, the reason I do the handout is just so you have really good pictures of what's going on, and also just to circumvent some of the length of how to do this problem. So this is for n equal 1, right? I'm picking one piece of paper. Now, what if I were to pick 2 slips of paper at a time? And who remembers, what is it that I want to actually keep track of then? What do I actually want to plot? The what of those 2 pieces of paper? The average, right? The sample mean. So I want to take, just like I was doing in Florida, I was saying taking the average of 20 people at a time, 30 people at a time, right? I don't want to just plot single pieces of paper. I want to plot 2 at a time. What's the average I would expect to get? Right. So give me one possible, what's like the smallest average you could get? And you're able to do this with replacement, right? So what's the smallest? Yeah, what would that come from if you pick?
1 and 1.
And what's the X bar for that? That'll be an average of 1. What else could happen? What's like the next thing up from that? 1, 2. And that would have an average of 1.5, right? You guys with me? And of course 1, 3, 1, 4, then 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2. You can at least see how it would be set up, right? Okay, so let me give you this handout. Let's see what happens when you do this. All right, so at first glance, the reason I want to do some of this on the board is so when you see this, there's something that's familiar. So we just did that up here on the board. This looks a little neater on here because I had Excel make it for me, right? So you guys see the same thing we just did, xp of x. What I did then after this is, for one thing, I calculated the average as 2.5. And how do you calculate the average in this case? There's actually 2 ways I would take. How would you calculate the average here? Do x times p of x and then add them all up. Since they're all equally likely, though, that's the only time you're allowed to just average these directly. They're all equally likely. Nobody's more likely than somebody else. So what is the average of 1, 2, 3, 4? 2.5. Only when they're all equally likely. But like he said, you could do x, p of x, add them up, that's the average. Now how do you get the standard deviation? Who remembers? That was one more column on there, right? X squared p of x, and then you throw that into the formula. So that's all I did to get those. So the mean is 2.5. The standard deviation for this is 1.118. So if you did that x p of x column, you can verify that that's true. Cool? So that's chapter 5 stuff. Now, what I did was I continued this idea down here. If you take a sample 1, 1, the mean would be 1. 1, 2, the mean is 1.5, and so forth. Yes, ma'am?
What does the sample 1, 1 mean?
So if I'm picking 2 things from a hat with replacement, and I want to do this kind of in an order, you could just start saying, well, I could get a 2 and a 3, or I could get a 4 and a 1.
But isn't there only one of each one?
With replacement. With replacement. So if you pick one, you put it back in, you pick another one.
Okay.
Yep. So when you start taking samples of size, whatever, your data now is the means of those samples, right? Our data right here are the actual numbers on the pieces of paper. When you start taking samples of size 2, size 3, size 80, it's going to be the average of everything you picked. So that's why I put that in try to highlight it. And of course my color printer is not working, so that's too bad for us. But they're highlighted all the means. Right? So for example, who can tell me, well, how many means are there? 16. What's the probability that you would get a mean of 1.5? 2 out of 16, because there's 2 1.5s, right? They're all equally likely, well, each individual one, but to get 2.5 and 1.5, it happens twice, that's 2 out of 16, that's 1/8 chance. So you can see then where this other thing came from. So here's the samples I could possibly pick, right? Here's all the averages from picking those samples, and here is what we just did up here. 1 only happens 1 out of 16. 1.5, like we just said, happens 2 out of 16 times, right? And so forth. Look at the picture now when I draw it. The most likely thing, of course, like we know, what's the most likely thing gotta be? It's the average. It's the expected value. And sure enough, 2.5 has a chance of 4 out of 16. It has a 1/4 chance still. Whereas I've introduced these new values in here that I didn't have before. Since it's averages, they don't have to be whole numbers. So look at the picture now. Is that more normal now?
Yes.
Hell yeah. So I even have, I think, being the geek that I am, I took it out one more time and I just did this on Excel. This would be picking at 3 slips of paper with replacements. So you can get 111, 112, 121, 122, 133, whatever, right? It would look like this. That's even more normal. If I did 5, it'd be even more normal. 20, 30 is definitely normal. But this is a really good example. Uniform is already kind of nice, right? Uniform is beautiful. It's symmetric already. So I don't need 30 to make it look normal. 2, it looks normal already. 2, it looks pretty damn normal already, right? Now here's the big thing. How are we doing so far? I mean, that sort of is a concrete example of what I did up here with this theoretical ages of people in Florida, right? That's sort of very abstract. So the really interesting thing, that's pretty interesting by itself. You can kind of make something normal by taking a certain sample size, right? Make the new picture normal. The mean for these, what do you think it should be? I mean, it says it right there, but why does that make sense? If there's an average age in here of 23, would that change just because I start taking 2 people at a time and averaging and then average all the averages? Could it possibly change from 23? Think about it. It's still all the same people. If I take all the samples of size 2 from everybody and then averaged all those averages, it still has to be 23, doesn't it? Still the same numbers. So the average for any of these will always be the same as what it used to be. The average can't change. The thing that will change, like we saw earlier, was the standard deviation change. They got in skinny, skinny, skinny. It really got in tight. So standard deviation gets smaller and smaller. And here's the ultimate cool thing, right? Here's the real nuts and bolts to this. So here's my symbol for mean of individuals. And in fact, I'll show you something here in a minute. What should be my symbol for mean of sample means? I have to have some kind of a way to denote it to show you that it's not just a mean of individuals. It's a mean, and I have it up there, so it's a good thing to look at. It's a mean of sample means. So believe it or not, you guys already have been exposed to subscripts. That just means a specific type of thing. So one of the first places you guys see subscripts is here. You guys remember that? Slope. What's that 2 mean? It's the y from the second data point, right? From the second point. So that 2 means a specific y. This x bar means the mean that came from the sample means. How are we doing? So that would be the mean I get when I average up all of these guys. Right? That's the mean of the sample means. Cool. Maybe. So this will always be the same. The mean can't change just because I take 5 people at a time instead of 1. How could I change the average that way? That's impossible. It's going to be the same average, of course. The thing that changes, though, the standard deviation of the sample means gets smaller. And it gets smaller exactly like this. The old standard deviation divided by the square root of how many things you picked. Let me say it all again here real quick. We know from earlier that when I start taking samples of size whatever, the mean becomes much more likely. So everything kind of goes closer and closer to the average. We know that means the standard deviation must be getting smaller then, because the standard deviation measures how far away you are from the average, on average, right? So if I'm getting closer, this guy must be getting smaller. This is just the formula that tells you exactly how small it gets. And like I said earlier, the bigger your n gets, the more slips of paper I picked, the smaller the new standard deviation gets, the closer it gets. So really what that goes along with is, if you weren't sure the average age of gross fund, and you picked 5 people, would that make you really sure about the average age? No. The more people you pick, the closer you should be getting to the actual average. Isn't that really what that stupid thing is saying, right? The more people you pick, the less off you are from the actual average. That's what that says. Yes, ma'am.
Okay, you said that you got your, the standard deviation from the average over there?
I got the standard deviation. Here's the original standard deviation, right?
Right.
And I got that from doing the x squared p of x. Remember we did that from
Yes.
chapter 5? Cool?
Yeah.
Here's the standard deviation for this situation. And again, same way. Do the x squared p of x thing. I get a standard deviation of 0.791. And if you check it, what is 1.118? So for us, it should be 1.118 divided by square root of what? I'm picking 2 slips of paper, right? So divided by square root of 2. What is that? .791, right? So again, the funny thing is, at this point you guys are either so freaked out or so bored, you don't really see what's going on. But this is actually, unfortunately, it's probably the best I could do with this because it's kind of freaky to get a hold of this. But it's kind of cool to see. I don't care what numbers you pick. You can pick whatever the freak numbers you want, however many you want. Pick as many of them at a time as you want. No matter what you do, when you calculate the new standard deviation, it will be the old one divided by the square root of how many things you picked. Always. I don't care what you make it look like, what numbers you pick, what probabilities you pick. I don't care. This will always be true. So I think one thing that will help us is to see this actually in action. Let's see a true problem then, what this looks like. So like I said, the concept took me forever to explain, and I feel like about half of you don't quite feel good with it right now. And that's fine, you shouldn't, because it's the first day we've talked about it. But if we do an actual problem, I'll show you how what changes in a problem is so minimal. It's kind of crazy. So here we go. Let me come over here for once here. All right. Let's see. Gas prices. What is it right now? I mean, put gas in my car forever. $3.89 is like a decent price, right?
79,
$3.79.
Yes.
You know, you go to Arco,
Yeah.
you pay with cash. And let's say standard deviation is, let's say, 13 cents. Just because. That's why having a building in a parking lot is not a good idea. So part A is going to be old news. Part A, I'm going to ask you, if you pick one gas station, and one thing I got to tell you here is that they're normally distributed. Let's say that they are normal, right? If I don't tell you that, you can't do the problem. Thank God. So if you pick one station, one gas station, what's the probability that their price will be more than $4? That's a problem you can do right now, no problem. This is a section 6.3 problem before we did any of this weirdness, right? So try that problem out. It'll be a nice review. This is what I call a classic z-score problem. No tweaks yet. Okay, let's find out. So what goes right in the middle? 3.7911, and then $4 is somewhere up here, right? And I want greater than that. So you don't look up 4. Now this is where it gets evil. When the data points look like z-scores already, people look up 4 and get all freaked out because 4 isn't even on there. It's not a z-score yet, so of course. So z equals what?
1.6.
Sorry, so help me set it up first.
4.
Good. My data point minus the mean. It's always minus the mean divided by 0.13. And so you get, sorry, 1.62. Okay, so always truly round it to that second place, right? And when you look up 1.62, what do you get from that?
0.9474.
Sorry? 9474? And so how do we get what we actually want?
Track from 1.
Yeah, 1 minus that, right? So you get 0.0526. Cool. So just over 5% chance, right? So you'd say just over 5% of the gas stations would be trying to sell it at $4 or more, right? Always surprised. There's always a gas station that's got like 50 cents above the price I buy it at. I'm like, who the hell's going there? So part B to this kind of question, this is exactly the way I love to do this question. So I'll be just like this on a test. I'll have a situation where I pick one gas station, so that's not different. Nothing's changed. What tells me when to do this weird shit is when I take a sample and I ask you about the sample mean. Those two things together make a trigger. Let's say, oh crap, I've got to do something different.
But it's still normal.
Exactly, it's still normal. The funny thing is, if it starts off normal, how big of a sample do I need to make it normal? 1, it's already normal. If by taking a sample, it makes it more and more normal as my sample gets larger, if it's already normal, it's just always going to be normal, right? It's the problems where they don't say it's normal. Then they have to have a sample above 30. If they don't have a sample of 30, you're allowed to say, I can't do shit with this, and then move on, right? Because you can't. If they don't tell you it's normal and they don't have a sample big enough, we can't do anything yet. What we can do is coming, but yeah. Okay, cool. So part B would say this. Part B would say we pick 6 gas stations. What's the probability that the mean from those 6 stations is more than $4? So how do I know when to do this weird stuff here? How do I know when the standard deviation must change? When I take a sample and I ask about the sample mean. That's when I know I have to change my standard deviation. And that's the only thing that changes. Everything else stays the same. So my first step here would be, what's the new standard deviation that I have to use? It's going to be the old one divided by square root of 6. So what was the old standard deviation? 0.13. Divided by square root of how many gas stations I'm picking. So I'm picking 6 gas stations, right? So somebody help me out there.
0.053.
0.053. And let me say this right now. I have to be really careful. When I say 3 places, I mean 3 non-zero places. Cool? So 0.053, 1. Okay. So you get 3 nice If there's 0, 0, 0, 0, keep going out until you get 3 nice numbers in a row there, right? So how are we doing there? Is that cool? And now you do exactly what we just did here. Just using, instead of 0.13, you use 0.0531. This standard deviation here, that standard deviation is only good for individual gas stations. They only tell me how far individual gas stations are from the average. I need something that tells me for 6 gas stations, so I must change the standard deviation into the new one. Do you guys see how to look at this? That standard deviation is good for individuals. I need the one that's good for groups of size 6 in this case. Okay.
But now, what'd you say we have to do with that number?
That's the only tweak. So now what do? We do exactly what we did up here. Same stuff we did. We make a z-score and we look it up. It's just that instead of 0.13 on the bottom, I've got 0.0531 on the bottom. That's it. So what's the z-score going to be for this now? Oops. So part B, still the same thing. I've still got 3.79 here. One above 4. 4 minus 3.79 divided by 0.0531. What do you get? Beautiful. Something like that, right? Are you guys getting that?
I have a question.
Yes.
When you get the 0.0531, do you use that as your area and find the z-score? No?
What is 0.0531? Oh, there you are. I thought you were going to come at the beginning. What is the 0.0531? What is that?
That's the new standard.
That's the new standard deviation, exactly.
Okay.
So
Okay,
to make a z-score, I've got to use the standard deviation I have. We have to use the right one. That's the one for groups of size 6.
okay.
So now what do I do once I get this? This is where I kind of purposely made this come out to something not on your chart. That's not on your chart, right?
Well, yeah.
Sort of. It goes up to what? 3.5. So then how much is out here then? What's it say about down here?
99.
Yeah, 0.9999? So above it would be about what?
0.00001.
I love it. So this would be 0.9999 officially by the book, and this will be 0.0001, just 1 minus that. I always say it's about 0%. So sort of like that 0 plus we saw with the binomial. Because the further I go out, the smaller and smaller it gets. It's basically getting closer and closer to 0. So I don't want to say 0.0001 forever. That's not really true. But if you do, I understand, because that's what the book says. So now, any questions about that? Yeah.
So basically, it means that if I pick 6 gas stations in a row, and all of them, and all prices would be more than 4, the probability is 0. Is that it's like very
The
unlikely
probability of picking 6 gas stations
that have
and
the-
finding that their average price is more than $4 would be about impossible, nearly impossible. It's getting pretty close to 0 chance, right? So if I did pick 6 gas stations and they did have an average price of more than 4, that might be evidence that the average isn't right. Because it's really, really unlikely to do that unless my average is wrong in the first place. And that's actually going to be Chapter 8. We'll get there eventually. Yeah. All right, so let me turn you over to Corey. He's going to pass out the evals. I'm going to be back in my office if you want to come catch me and ask me anything. Okay?
Does that work okay for you, Jeff? I figured this way you could split.
Yeah, it's fine.
At the end?
Yeah, it's fine.
Did I say in my email I was coming to you?
No.
Oh, okay.
I figured you might be since I didn't see it first yet.
Oh, sorry about that. How's it going, guys? I'm Corey Manchester from the math department, and what I'm here to do is allow you the opportunity to do your student evals on this class and Jeff over here. So if you would just kind of hang out for a few minutes, take your time to give some thoughtful responses to these questions, and then when you're done, I'll get them all collected. Don't put your name on these forms. Basically, all you're going to fill in. All you're going to fill in is Jeff's name, the